Hey everyone! In this video, I would like to talk about the second derivative test. So the second derivative test is going to give us another way for us to identify any local maximums or minimums for a function. So let's start by reading through the test. It says, let f be a function for which the first derivative and the second derivative exist on an open interval from a to b. So that's important. We need the first and the second derivative to exist. If they don't, we actually can't use the second derivative test. And then suppose that c lies in this interval from a to b and is a critical number of f. All right, so because c is a critical number, right away that does tell me that at c we have a horizontal tangent line. And then the test, if the second derivative at c is less than 0, then that point is going to be a local maximum. Or if the second derivative at c is greater than 0, then that point is a local minimum value. So let's just think about what this is saying. And I'm going to just sketch out a couple graphs here. So I'm going to say I have a curve like this. And it'll keep going. So at this point, so let's say that this is c, and we have a horizontal tangent line here. We know this because in our description, we are given that c is a critical number, so we have a horizontal tangent line. So then at this point here, this is the point c and f of c. Now in this case, our second derivative, so f double prime of c, is less than 0. And the reason that this creates a local maximum value, so our second derivative is less than 0, which means it's negative, which means that the rate of change of our first derivative is negative, it's going down. So that means that the slopes of our tangent lines are starting to decrease. So as I go from left to right, you can see here that this tangent line, if I were to slide this along, it would start to decrease. Right now it's at 0, but it's going to start being negative as soon as I move to the right of my critical number. Now if I take a look at the opposite case, so now let's take a look at our local minimum. So here, it's another value c. We have another horizontal tangent line at this point. And now in this case, at this point, our second derivative is going to be greater than 0. And same logic, but now it's just reversed. So the second derivative indicates the rate of change of the first derivative. The first derivative indicates the slopes of our tangent lines. So as I move from left to right, so as I go just on the other side of c, the slopes of my tangent lines are going to start increasing. At c, the slope is 0. But as soon as I move beyond that, I'm going to start getting positive slopes. So they're increasing. So that indicates we have a local minimum value. So that's the general idea for the second derivative test. So what we need to do is we'll locate critical numbers. And then at those critical numbers, we'll use the second derivative to find out if it's positive or negative, which then in turn indicates if we have a maximum or minimum value. So now let's take a look at an example. And I'd like to do a couple different things with this. I want to find where this is concave up or down. I want to find inflection points. And then lastly, let's use the second derivative test to find any local extrema. So the first thing, if I want to determine concavity, I am going to need the second derivative. So let's find that right away. So our first derivative will have 3x squared minus 12. And then the plus 10 here, so the derivative of 10 is going to be 0. And then our second derivative, we have 6x to the first, and then the derivative of negative 12, we just get 0. So now taking this and setting it equal to 0, this will indicate where we have inflection points. So it just looks like we have 1 at 0. That also indicates the intervals, which we're going to take our domain and we'll split it up. So let's think about a sign chart. So we have two intervals to take a look at. We have the interval from negative infinity to 0, and from 0 to infinity. Now, the test for concavity, we're going to test these intervals to see where our second derivative is positive and where it's negative. So if I plug in a negative number, 6 times a negative, we get a negative. So everything to the left of 0, my function is concave down. And now if I plug in a positive, 6 times a positive, we get a positive number. So that means everything to the right of 0, my function is going to be concave up. So let's just summarize that right away. So our function is concave down on the interval from negative infinity to 0. It's concave up on the interval from 0 to infinity. And then that means at 0, at this x value, we are going to have an inflection point. And if I take 0 and I plug it back into my original function, f of 0, we end up with 10. So I get an inflection point of 0, 10. All right, so that takes care of the first two things I wanted to do. We know where our function's concave down, where it's concave up, and we know where we have an inflection point. Now the next thing I want to do is I want to find any local minimum values or local maximum values. So to do that, we do need our critical numbers. So I'm going to go back to my first derivative, and I'm going to set that equal to 0. So 3x squared minus 12. And if we factor this, I can factor out a 3, leave me with x squared minus 4. And to finish factoring, we get x plus 2 and x minus 2. So our two critical numbers, we have one at x is equal to negative 2, and our second critical number at x is equal to positive 2. Now to find our local extrema, we're going to take both of those and we'll use the second derivative test. So we'll take the second derivative and we'll plug in 2. 6 times negative 2, we get negative 12. And then the second derivative at positive 2, 6 times 2, we get positive 12. So if our second derivative is negative, that's going to indicate a local maximum. And if our second derivative is positive, that's going to locate a local minimum. And why don't we find our function values at these two x values just so we can be more specific when we indicate our local extrema. So at f of negative 2, we're going to have negative 8, negative 12 times negative 2, that's going to be plus 24, plus 10. So overall, that's going to be 26. And then for f of 2, we'll have 8 minus 24 plus 10, which is going to end up giving me negative 6. So we can summarize then. So we have a local maximum at the point negative 2, 26. And we have a local minimum at the point 2, negative 6. So using the second derivative, we were able to get a lot of information. We were able to determine where it's concave down, where it's concave up. We were able to determine where we have inflection points. And we can also use the second derivative test to determine where our local maximums or local minimums are. And to finish up, why don't we just take a look at the graph of this function just to verify what we found. So to type this in, go to y equals, and then we have x cubed minus 12x and plus 10. And now I do want to double check my window. So we know we have a local maximum at negative 2, a local minimum at positive 2. So I want to make sure I get those in there. Our inflection point's at 0, so that's within that range as well. So I'm going to go a little bit to the left of negative 2, a little bit to the right of positive 2. And now taking a look at our maximum and minimum, so we need to, for our y values, we need to get positive 26, and we also need to get negative 6 in there. So I'm going to go from negative 8, a little bit below negative 6, and I'll go to 28, a little bit above our maximum. And if we graph this, we should be able to see everything. And we can tell. So we have our local max at -2, and we have a local minimum at +2, and then our inflection point occurs at 0. So everywhere to the left of 0, our function is bending downwards, so it's concave down. And then at 0, that switches, so that's our inflection point. And now everything to the right of 0, our function is bending upwards, so indicating concave up. So again, the second derivative test, it's another way that we can find local extrema, but overall, the second derivative does give us a lot of information about the graph of a function.